We're actually going to use the process that we did yesterday where we wrote the p sub k plus 1 term, and we're going to use that to help us write proofs of mathematical induction. I have 2 or 3 examples that I can do. Ideally, I'd like to do 2 of them with you and then give you some time to get started on your first homework assignment so we can kind of check as we go. But if we feel like a third example would be beneficial, we can certainly do a third example together before you start your homework assignment. And what I'd like for you to be thinking about as we do our 2 proofs today in our examples is we're going to structure them the same way. So even though our proofs can be slightly different from another proof, because the way you write proofs is a little bit different, what's nice about the ones that we're doing in this particular chapter is it gives you an entry into mathematical induction, but really we're all going to come up with basically the same proof aside from like a few maybe changes in wording here and there. Okay, but other than that, we'll all kind of be doing the same thing. The first slide that I'm going to show you is the slide from yesterday, and you should already have this in your notes, so I wouldn't take the time to rewrite it. This is in the textbook. If you go to section 9.4, you can find it in a box, the principle of mathematical induction. But we talked about this yesterday in that how the mathematical induction proof works is we prove for the first case, and then we start the domino effect. We also prove that a previous case, the truth of a previous case implies the truth of the next case, therefore knocking down all the dominoes and proving all of our cases. Okay, so that's like the basic gist or idea of mathematical induction. So what I did on this slide is I kind of took what that principle of mathematical induction says mathematically, and I'm going to kind of say like how it's going to work for us in our proof. So this is more like in our own words, on our terms, describing principle of mathematical induction. So this might be helpful to jot down some of these tips or reminders in your notebooks. Okay, so how it works. There is a base step that needs to be always completed in a mathematical induction proof. Can't leave this step out. And this step is where you verify the formula for n equals 1. So we assume that we're always starting with the first term where n is equal to 1. If you were to ever cross a mathematical induction proof and it said it had a statement or a constraint after this statement that said, comma, like n is greater than or equal to 2, then you would change your base step. You wouldn't verify for n equals 1, you'd verify for n equals 2, the lowest that n could ever be. Okay, but most of the time it doesn't say anything like that, so we always just assume the first term, n equals 1. Okay, so that's the base step. This you're going to see is a very easy step to do, and you're just going to be like, yep, it works in a matter of seconds. Okay, but you have to show that step. The second step is the induction step. And the induction step takes a little bit more work, and this is where we actually get to the proof of it. So in the induction step, we're going to assume that the formula we're being asked to prove is true when n equals k. So in the second step, you've already proven the first case, okay, for n equals 1. In the second step, you're going to assume the truth for n equals k. Then, after you assume it's true, you have to also show that s sub k plus 1 is true. Okay, so you're assuming it's true for n equals k, then you're going to show that it's true for the next term, setting off that domino effect, where then we can just knock down consecutive terms and prove all the cases. Now notice I'm using this notation s sub k plus 1. That's a little bit different than what we did in our homework assignment where we were doing p sub k plus 1. So the idea here is we've just finished a sequence and series. When we use a capital S with the subscript notation, we're implying series. So we want to show that the sum of the first k plus 1 terms is this formula, okay, and that the truth of the previous one implies the truth of the next one. This is more notation, right? The series, so the sum of the first k terms plus a sub k plus what? So this again is a series. This is the k plus 1 term, so then you're using a sequence. So it will be helpful to you in the work, in the proof, if you can distinguish between what is the formula for the series, the sum of all the terms, and what is the formula for the sequence, just the number of terms that it is. And I'll try to point that out when you do our example. Any questions on that before we actually do an example? Okay. If we can get those two things to work out, then we can make a statement that this is true for all cases. Here's our first example. We're going to be asked to prove 1 plus 3 plus 5 plus 7, so on and so on, plus 2n minus 1 is equal to n squared for all n greater than or equal to 1. So you can use mathematical induction in cases beyond sequence and series, but all the questions that you'll be asking in this chapter revolve around the sequence or series. They're all going to kind of look the same. Notice that what you're seeing right here, 1 plus 3 plus 5 plus 7, you could continue that, right? Plus 9 plus 11 plus 13. It's the sum of the terms in a sequence. And that sequence is all of the odd numbers, correct? Okay. So this statement right here, this is what I'm talking about. It's important for you to be able to determine the difference between this formula for the series and the formula for the sequence. 2n minus 1 is how I would get a term in the sequence. So this is like my a sub n, where if I want to add the first 50 numbers, I would do 2 times 50 is 100 minus 1 is 99. So I would be adding all the way up to 99. This n squared, to say that 1 plus 3 plus 5 plus 7 plus dot 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 to n minus 1 is equal to n squared. N squared is the formula for the series. It's the S of n. So keep that in mind as we work through the proof. One is finding a term in the sequence. One is finding a sum of the series. Okay, we're going to start by sounding like a mathematician here, and we're going to make a statement that basically rewrites the question. But we're going to say, let S sub n equal 1 plus 3 plus 5 plus 7 plus 2n minus 1. So we're saying let the series be the sum of all the odd or positive odd integers. And let's say that it is in fact n squared for all n's greater than or equal to 1. So you'll start every proof, induction proof, kind of like with this same statement where you just say, let S sub n equal, and then you basically copy down the problem. Okay. We're going to start with our first step, which is our base step. We're going to show what the sum of the first term is using that formula. So the sum of the first term, remember the sum of the series is n squared. The sum of the first term then would be 1 squared, which is equal to 1, if you were to go back to the series and add up only one term, is that your actual sum of one term? 1? Yeah, if you only had the first term 1 and you calculated the sum of the series would be 1. So I usually say something like s sub 1 equals 1 squared, which equals 1, which is true. Now, you don't have to write that which is true statement if you don't want to. I always like to say, okay, otherwise what am I saying, right? But I always like to say, yes, that's true, I confirm that. Okay, so you don't have to write that if you don't want to. You could leave it as s sub 1 equals 1 squared equals 1, and anybody could look back at the first term and see that that's true. Okay, so you did the base step. Induction step. Remember, the induction step has two parts. The first part of the induction step always starts with an assumption. So you can always start step 2 by saying assume. And what we're going to do is we're going to take this series formula, this s sub n equals n squared, we're going to assume it's true when n equals k. So we're basically going to copy this line again, replacing all the n's with k's. So we're going to say, assume s sub k is equal to 1 plus 3 plus 5 plus 7, all the way to 2k minus 1, whatever that k term is equal to k squared for all k greater than or equal to 1. Okay, so I've basically copied the same thing I started with, just replacing n's with k's. And that's the first part of the induction step. Okay. Now, eventually we're going to be asked in the second part of the induction step to do s sub k plus 1. But in this assumption, we want to get a statement so I know when I finish my proof. Right? And that's what you guys practiced yesterday. You wrote out the piece of k's. You had the piece of k's, and then you wrote out the piece of k plus 1. We want to know, given that formula for the series, what is that formula for s sub k plus 1? If I can then algebraically get to that formula, I will have made a proof. Okay? So we want to show that s sub k plus 1 is equal to, and then think about up here in your assumption, you assumed s sub k was equal to k squared, right? Okay, you want to use the formula for the series, not the formula for the sequence. What would then s sub k plus 1 be for k squared? K plus 1 squared. Show that. If you can show me that the sum of the first k plus 1 terms is k plus 1 squared, then you'll have shown me that the truth of s sub k implies the truth of s sub k plus 1, and therefore creates a domino effect. Okay. So this is where you're doing the work from yesterday. You're practicing plugging in your k plus 1. Okay, now we're actually going to verify that algebraically. So I'm going to say s sub k plus 1 is equal to, and if I said add up the first 50 terms, what would you do? 1 plus 3 plus 5 plus 7 plus 9 plus 11 plus 13 plus 50 until you've done 50 of them. Okay, so we're going to write that out again. And I would go all the way up till, 99, 2 times 50 minus 1. This right here that I've written down is just s sub k. Right? That's what s sub k is equal to. 1 all the way to 2k minus 1. In order to get s sub k plus 1, I'm going to have to add the next term. So to add the next term, think back up to the beginning here. To find the next term, the a sub k plus 1, you'd be plugging into the rule for a sub n, which is that 2n minus 1 or 2k minus 1. Okay. So now, to get a sub k plus 1, you are going to do 2 times k plus 1 minus 1. I'm using the rule for a term in a sequence. And I'm finding the k plus 1 term. If I found the 50th term, I would plug 50 in there. If I want the k plus 1 term, I've got to plug k plus 1 in there. Okay. If you simplify this, what do you get? 2k plus 2 minus 1, so that's really 2k plus 1. So the k plus 1 term is 2k plus 1. You're plugging that into the formula for the sequence, not the series. Okay, is everybody okay with what I've done so far? Does anybody have any questions? Where anything came from? Okay, so make sure you have your attention focused here, and so you know where this what always happens next. So you have copied down S sub k. You have already assumed what S sub k is equal to. S sub k is k squared. So I can take all of this stuff, 1 plus 3 plus 5 plus 7 plus 2k minus 1, and I can replace it with k squared. We showed that that worked for the first term, and then we assumed it for n equals k. I still have to add to it the next term, so plus 2k plus 1. So this is S sub k plus a sub k plus 1. I now notice I have a trinomial, it's quadratic. I'm going to check if I can factor it. Can you factor k squared plus 2k plus 1? What does it factor out to be? What's that? Oh, k plus 1 squared. And so we're saying S sub k plus 1 is equal to k plus 1 squared. Is that what we wanted to show? Yep. So we've made a proof. We have shown that it works for the first step. And then we assumed that it worked for n equals k. We showed that if it works for n equals k, it also works for k plus 1. Therefore, it knocks down all the dominoes. The first one's going to imply the second one, the second implies the third, so on, and we have truth. The final thing to do to wrap up your proof is make a statement. Thus, the statement is true for all positive integers. And you could say for all positive integers, or you could say for all n greater than or equal to 1. Those two things mean the same thing. Okay, thus the statement is true. You can also be more descriptive in that statement. You could say thus S sub n equals 1 plus 3 plus 5 plus 7 plus 2n minus 1 equals n squared is true for all positive integers. But at that point, I feel like we don't need to say that again.
How do you know what you want to show?
Because that's the work you did yesterday. So you copy down that series formula of replacing it with k's, and then you do the k plus 1 series, which is what you did yesterday. And that tells you, like, when you get to that at the end of your proof, you know you're done. Good question. Any other questions? Yes, we're going to do another one. I think the muddiest part for most students is like right in here. Okay, and this is what I'm saying, like, be very careful when you add that extra piece. You need to add the term in the sequence, so you got to go back up to the sequence rule, not the series rule. Okay, but otherwise we're focused on the series rule. Okay, that's the one time we use the sequence. Okay, let's try another one. We're going to prove that 2 plus 7 plus 12 plus 17 plus dot 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 plus 5n minus 3 is equal to n divided by 2 times 5n minus 1. Okay. Again, I think it's worthwhile, especially in the very beginning, to make sense of what we're talking about. That whole piece where we're doing 2 plus 7 plus 12 plus 17, that's adding up terms in a sequence. It must be an arithmetic sequence because they're all going up by 5, a common difference. And then 5n minus 3, that's the rule for my sequence. So that's like an a sub n. So that if I want the third term in my sequence, 5 times 3 is 15, minus 3 is 12, and certainly 12 is my third term. Okay, so I'm eventually going to use that rule to get my k plus 1 term. And then this piece right here, n over 2 times the quantity 5n minus 1, that's what the sum of all those things are, so that represents my s sub n. S sub n. And you can make some connections here back to like section 9.2, that formula for the series, the arithmetic series, this is that formula, okay, with n's. Okay, so start with your statement to get your proof started. Let S sub n equal, copy the problem, 2 plus 7 plus 12 plus 17 plus 5n minus 3 equal n squared, or n divided by 2 times 5n minus 1. This one doesn't say for n greater than or equal to 1, so we're just always, now since it doesn't say, we'll just assume we start at the first one. Okay. So I'm going to do my base step. S sub 1 should equal, and we're going to plug into the series formula. So I'm going to replace all the n's with 1s. 1 over 2 times 5 times 1 minus 1. Which is 1 over 2 times 4, which is 2. So we're saying the sum of the first term is 2. Do you agree with that in the sequence if you only had one term? Yeah, so true. This does not have to be written, okay, but if you want to say, okay, that's true, you can write that.
What would we do if it's not true?
Then your rule doesn't work for your first case counterexample. Stop proving,
Oh, okay.
right? Will that be the case? No, because I want you to write the proof. So I'm giving you things that are actually true, right? So the first step should always work out.
Why did you pick the very easy?
I was just showing that this a sub n right here, 5n minus 3, if I put 3 in for n, 5 times 3 is 15, minus 3 is 12, it's just generating the terms in the sequence. To show that that formula, that 5n minus 3, is not the sum of the series, it's just the terms in the sequence. Okay, step 2, inductive step. Always start inductive step with assume. We're going to assume that S sub k is equal to 2 plus 7 plus 12 plus 17 plus 5k minus 3, and that's equal to k divided by 2 times 5k minus 1. Okay. We've already shown that it works for the first step. We're now going to assume that it works for k's. If we can show that it works for k plus 1, then we're creating that domino effect, where one knocks down the other. Okay? So then I want to know, like, well, how far am I going to go in my work? I've got to pick out that s sub k plus 1. So this show that piece is what you did in your homework yesterday. Now, the difference between yesterday and today is there's a little bit of stuff in the middle. So S sub k is the sum of all the terms in the sequence, but we're saying that its formula is k over 2 times 5k minus 1. So we want to plug k plus 1 in for those k's in the series formula. And go ahead and do that and see if yours show that is going to look the same as mine. What's your S sub k plus 1? If you plug k plus 1 in for both k's. What does yours look like? We'll see if you get the same answer as me. Doing a little bit of work off to the side. You can do it in your proof, or you can do it like kind of in the margins if you don't want it to mess up your proof. I'd have to distribute 5k plus 5 and then subtract 4, so I'm getting 5k plus 4. K plus 1 divided by 2 times 5k plus 4. Is that what your S sub k plus 1 looks like? Okay. Okay. So if we can get down to that, then we'll know we have a true statement, and that we'll prove the formula for all of the cases. Okay. So now we've actually get down to the nitty gritty and actually prove that. So you got to start with S sub k plus 1. If you were going to do the sum of the first k plus 1 terms, you would start with the first term plus the second term plus the third term. So we're going to copy down all of that stuff. 2 plus 7 plus 12 plus 17 plus 5k minus 3 This is S sub k, or the sum of the first k terms. We really want the sum of the first k plus 1 terms, so we have to add the k plus 1 term. To add the k plus 1 term, remember 5k minus 3 is like your rule for the sequence. So that's the rule for the k term. You want to plug in k plus 1 so you can get the k plus 1. So again, I'll do a little bit of work over here. 5 times k plus 1 minus 3. That's 5k plus 5 minus 3. So I'm getting plus 5k plus 2. So remember here, this is the part where you use the rule for the sequence, not the rule for the series. Okay? Now, really important, all of this is S sub k. What did you just assume S sub k was? K over 2 times 5k minus 1. We just assumed that S sub k in the green boxes is this formula. So I can take all of this work right here and reduce it to that formula. Okay, I made that assumption, so I can now use it with substitution. K over 2 times 5k minus 1. You're always going to take that first part where you're adding up all the terms in the series, and you're going to set it equal to what you assumed the series was, that formula with k. You still need to add 5k plus 2. Now, one thing I recognize, like over here on the left, I could distribute the k, and that would give me like 5k squared minus k over 2. And I want to add 5k plus 2. In order to be able to add those, I need common denominators, correct? Okay, this is really like 5k over 1, or sorry, 5k plus 2 over 1. So I'm going to need to multiply this by a 2 over 2. So I can have one denominator of 2. Okay, and I can add this up in the numerator. From the first one, I have 5k squared minus k, and then I have 10k plus 4, because I'm multiplying it by 2 over 2 to get common denominators. So at this point, you're not really like so much in the proofing nature, you're just in algebra. And you need to think about, like, algebraically, how can I get these things to combine into one? Because the formula is one formula. If I simplify again, so I combine my like terms, I get 5k squared plus 9k plus 4 all over 2. And again, I'm to that point where I've done as much simplifying as I can, and now I've created a quadratic with 3 terms, a trinomial. I'm going to say, like, can I factor that? So if I were going to try to factor that, I would have 5k and a k as first terms in my binomials. That will give me my 5k squared. And then to get the 4 in the back, I need factors of 4, 1 and 4, or 2 and 2. If I use 2 and 2, I'll get 10k and 2k. Not helpful. That's 12k, not 9k. And so I'm thinking about 4 and 1. If I put 4 in the first one, 1 in the second one, I get 5k plus 4k, which is 9k. So however you factor, okay, I use guess and check. Well, I've got down to factored form 5k plus 4 times k plus 1 all over 2. Is that what you're looking for? Go back to your show that. Show that s sub k plus 1 is k plus 1 over 2 times 5k plus 4. Is that the same thing as 5k plus 4 times k plus 1 over 2? Yeah. So now you know you've gotten to that statement that you wanted to show. They are the same thing. So then we can say, thus the statement is true. Before we leave this, I want you to look it over. Are there any questions about where anything came from? Because it's important that you ask these questions if you're not sure where I got a number or a statement. We're okay? Okay, we have about 15 minutes left. Would you like to get started on the first problem in the assignment? I think that would be a good idea, so you kind of have one started and ready to go. Is that okay? Okay. So find the paper that's going to be your assignment. You've got 5 proofs to do. You have to do all of them. I would say they probably take up half a page, maybe more. They need a couple pages. And I'll get number 11 up here. So you can get started.